Mr. Brown, if you started the lesson, I think your microphone's muted.
Sorry about that, guys, at home. That was fun. So at home, we're just reviewing different things we have for limits. If I have a number over 0, we do know that that value is undefined, so the limit itself would be d and e. What if we have a number over infinity for a limit? What would that be? 0. We know when it's big on bottom, that limit is approaching 0. And then what about if we have something heading towards infinity times a number? What would that limit be? Infinity, or also you could say d and e. And then this last column, what did it mean when we had 0 over 0 for a limit? It was like weird stuff, right? So it was like indeterminate, and I think in the flow chart we just called it to keep going. And like our keep going options, we had like factor and cancel. We could rationalize. I just had the vague like other algebra, like if we needed to combine 2 fractions or get rid of fractions within fractions. What about if we had an infinity over infinity? What do we do for those problems with limits? So those were the cases also kind of keep going. Mainly the methods we use for those is like maybe we had to do what matters most, like figuring out there's multiple terms in that limit, which one was the most important one. Or if we were comparing the numerator with the denominator, doing flexible to figure out like which infinity was the bigger infinity. The other kind of strange indeterminate one is the one that I often think of as 0 times infinity. In math, it doesn't make sense to multiply 0 times an infinity. That is also what's considered an indeterminate form. So this was the other case where we had to keep going. We didn't see too much of this case in Unit 1. We'll see a little bit more with L'Hopital's rule. And when I do say 0 times infinity, sometimes mathematically that works out to being 0 times undefined, because you're basically going to be like multiple 0 times like where an asymptote's located for another factor. So when we're looking at limits, we saw all sorts of ways that we could evaluate. We spent a whole unit just evaluating limits. Today's kind of topic with L'Hopital's rule is going to be another way to evaluate all of these indeterminate cases. And I do want to be clear, some of those indeterminate cases, like you still want to use Unit 1 methods because it will be just as fast. Like if you can easily factor and cancel, then that's probably what I would keep on doing. But L'Hopital's rule is nice is because it will work for just about every indeterminate case that you can encounter. So it will just give you another option to do. Plus it's going to give us a whole nother way to evaluate limits that we couldn't do, of certain types of problems that we couldn't do back in Unit 1. So what does L'Hopital's rule states? There's Mr. L'Hopital. They all kind of look the same back then anyways. But I will say a little bit about L'Hopital's rule, some things that we have to be kind of careful with. Certain things, when College Board was creating the AP course, they get very, very picky about how students like show certain steps. Like for example, when we're doing intervals of increasing and decreasing, a sign chart is not your final answer. You have to go back and like justify it somehow with like words or clearly stating your answer. For L'Hopital's rule, there are some requirements that your problem has to include in order for you to be able to use L'Hopital's rule. And in order to receive full credit on the AP exam, you have to show those justifications. And I'll show you exactly how to do that. Like it's not difficult. But I do know as I was grading the AP exam this past summer, every year, almost guaranteed, there's going to be a free response question that has some L'Hopital question on it. And it's unfortunate, like you could work it out and get the right answer, but if you don't clearly show why you're using L'Hopital's rule, then you earn no credit. So it's just something that College Board is very, very kind of picky about. So I just want to do that disclaimer before we get started. Alex, you had a question?
Why wouldn't 0 times infinity be 0?
Because often 0 times infinity is not 0, because when we say infinity, that means it's often like approaching an asymptote. And so like we just kind of have some weird things in math when we say that something is approaching an asymptote. And you also have to be careful when I say 0, it doesn't mean that it is always equal to 0, it just means that it's approaching 0. So it's better instead of saying like 0 times infinity, think of something approaching 0 times something approaching infinity, and math doesn't always make sense. So what does L'Hopital's rule states? It is only used for kind of two main cases when you do direct substitution. And if you have direct substitution and you either get 0 over 0 or infinity over infinity, those are the only two cases you can use L'Hopital's rule. Now, sometimes you may rewrite a problem to force it to give you 0 over 0 or infinity over infinity. But those are the two main cases where we're going to use L'Hopital's rule. And what L'Hopital rule states is that if you get 0 over 0 or infinity over infinity, then the limit of the function, which we're always going to kind of think of it as a fraction, hence the 0 over 0 or infinity over infinity, the limit of the original function is going to be equivalent to the limit of the derivative of the numerator over the derivative of the denominator. Be careful here, this is not the quotient rule, like we're not taking the derivative of the function. We are just literally taking the derivative of the numerator and then taking the derivative of the denominator. And where the AP exam gets picky at is you have to clearly show that the limit of the numerator is going to 0 or infinity, and you have to clearly show that the limit of the denominator is going towards 0 and infinity. It's just some like notation you have to be careful with. But that is basically what L'Hopital's rule states and will allow us to do. Some things I will say also, whatever reason, once I teach L'Hopital's rule, I always have students who just want to make every limits question a L'Hopital's rule problem. But again, it only works when you have the indeterminate case. So like, if you're to plug in a number and it gives you a number, like doing L'Hopital's rule would end up giving you the wrong answer. So it only works when initially you have the indeterminate case. So as an example, I want to be able to like compare this to kind of like old stuff and new stuff. Here's a question that we very much did, probably the same one, if not very similar one, back in Unit 1. We know that when you're doing a limits question, what's the first thing you always want to do? Direct sub, always the first thing you want to do. Clearly, you rarely have one that just works out nicely, or else it wouldn't be AP calculus. So if you're looking at this one, your Unit 1 self would do what to kind of solve that limits question? Factor and then cancel. Like if I see two polynomials, we know how to factor and cancel. I don't want to discredit that method because it works. And in fact, if I'm being honest, this is probably the method I would use for this one just because it is really, really easy to factor and cancel. So I can plug it in. My x minus 6 terms factor, they factored out and then canceled. So this limit is really the simpler problem. The limit as x goes to 6 of x minus 1. Doing my direct substitution, and I get 5. I will never tell you which method you have to use when you're taking the limit. So like if you're good to go do the limit that way every time for this type of problem, then go ahead and do that. We can also, though, do this problem using L'Hopital's rule. And so for L'Hopital's rule, I'm going to go ahead and just rewrite the question here. On the AP exam, and same for like my test, you have to show clearly why you're using L'Hopital's rule. The easiest way to do this that will also still earn you full credit on the AP exam is you have to show that the numerator is approaching 0 or infinity, and you have to show that the denominator is approaching 0 or infinity. And to do that, you just need to use an arrow. No equal signs. You have to show clearly the numerator and denominator separately. So how I would show this numerator, after doing direct substitution, 6 squared minus 7 times 6 plus 6, that is going to give me 0. And then my denominator, 6 minus 6, is going to give me 0. That's the shortest way you can do that and still earn full credit. Things that would not earn full credit is if you just drew a single line showing that was 0 over 0. You're not showing clearly that the numerator and the denominator separately are both going to 0, so that would not be full credit. You also don't want to say equals 0 over 0. On the AP exam, that would not earn full credit because 0 over 0 is not an actual number. So you don't want to show those. You do need to use 2 arrows. The long way to show your work, so like if you want to be like super technical, guarantee, earn all your points in the AP exam, this will do it, but the long way to do the problem is you would have to kind of go off to the side and show that the limit of the numerator is equal to 0 and the limit of the denominator is equal to 0. That's the official math way to show it, but on the AP exam you are allowed to show numerators approaching 0 and the denominators approaching 0. So I've showed that, and so now I can go ahead and use L'Hopital's rule. And L'Hopital rule states that if I have an indeterminate case, then I can just take the derivative of the numerator and then take the derivative of the denominator. The derivative of the numerator is 2x minus 7. The derivative of the denominator is 1. Doing your direct substitution, 2 times 6 minus 7, 12 minus 7, which is going to give you 5. We get the same answer because obviously it is the same problem. I do think factoring and cancel is the easier way for this one, but that will at least let you see kind of the process for how L'Hopital's rule would work. Questions on that? All right, other examples. We're just going to run through a lot of examples for today. Here's 2 examples, both involving trig. One of these we were unable to do back in Unit 1. The other one we could have answered technically in Unit 1. And that's always going to kind of be where we're at. So for the rest of the time when we see a limit question, you can use Unit 1 options, or if possible, you can use L'Hopital's rule. Just kind of be up to you of which one's easiest. This first one would be one that you would be forced to use L'Hopital's rule on. Again, when you're doing a problem with L'Hopital's rule, you have to clearly show what the numerator is approaching and what the denominator is approaching. So the sign of 0 is 0, and then x is going to 0, so we have 0 over 0. So this is an example where we can do L'Hopital's rule. We were unable to do this one back in Unit 1. You can't like factor that, you can't cancel, there's no rationalizing, like it just is what it is. L'Hopital rule states that the derivative of each of your quotients, so the derivative of sine is cosine, the derivative of x is 1, and then now I can do direct substitution. The cosine of 0 is 1, and then we have 1 in the denominators. The limit to that question would be 1. The second one, you do have kind of 2 ways to do it. You could do it using L'Hopital's rule. What other methods could you use for that second limit question? Say again? You can use like FEPL, kind of like what matters most, right? So let's do it the Unit 1 version way first. If I want to do it the Unit 1 version, I can think about what matters most in the end behavior model. In Unit 1, we've had to ask ourselves kind of like in that numerator, what matters most, the 2x or the cosine of 3x? And which one would it be? 2x. Cosine is always stuck between -1 and +1, so you would have 2x. Well, what matters most in the denominator? X squared. This is going to simplify to 2 over x. Well, x is going towards infinity. So when your denominator goes to infinity, what is this limit going towards overall? 0. This is one where we could also do L'Hopital's rule. I'm going to be honest, I would probably not do this one using L'Hopital's rules. I think FEPL, what matters most, is the most efficient. But just to show you that other options still work using L'Hopital's rules. Show what the numerator and the denominator separately are approaching. So as x goes to infinity, we basically have like 2 times infinity plus a cosine. So that's just going to be going towards infinity. In my denominator, x squared is going to go towards infinity. Since I have infinity over infinity, I can use L'Hopital's rule. And L'Hopital rule states I just need to take the derivative separately of the numerator and the denominator. This becomes 2 minus the sine of 3x times 3. My denominator becomes 2x. Why I would avoid L'Hopital's rule for this one is you're still stuck doing kind of like what matters most. So like if I'm looking at this one, towards infinity we have 2 over 2x. because 3 times the sign is going to be stuck between -3 and 3. Either way, the denominator is still the x, so this limit is going to go towards 0. Same answer, kind of 2 different approaches. Obviously for this one, unit 1 stuff works best. And I do show you that one just because I don't want you to get in the habit of just always jumping to L'Hopital's rule when we just spent like a whole unit back in August of other efficient methods to use. So go ahead for me and try these 3 for me. Some of those use L'Hopital's rule. Some of those do not use L'Hopital's rule. Some of those use L'Hopital's rule, but you can do it other ways that we learned back in unit 1. So go ahead and try those 3. And I would just recommend getting in that habit of showing clearly what the numerator and the denominator is approaching.
On the test, are you ever going to give us questions that don't need many L'Hopital's?
Definitely. Like the homework tonight is unit 1 stuff and L'Hopital stuff. We always need to just be careful of seeing it. So this first one, I have the limit as x goes to pi of x minus pi over cosine of x. Looking at that numerator, pi minus pi is 0. The cosine of pi is -1. Is that going to be an example we need to use L'Hopital's rule for? Nope. So this one is no low. What would be the answer to that first one? 0. 0 over a number is just going to give us 0. And again, I show you that one because for whatever reason, once I teach L'Hopital's rule, students just want to make every question a L'Hopital problem. But if you were to actually do L'Hopital's rule for that problem, you would not get 0. You would get the incorrect answer. Looking at the second one, that numerator is always 4. Big clue that this one will automatically not be L'Hopital's rule. The denominator is going towards infinity. 4 over infinity, what is this limit going to be? 0. 4 over a huge number, that one's also going to go to 0. This last one, so I have the square root of 4 times 9, square root of 36 is 6 minus 6, so I have 0. 9 minus 9 is 0. This one, we can do it using L'Hopital's rule. If I didn't want to do L'Hopital's rule, what would be the other method I could use to solve that one? I have a square root in there, so probably what? Rationalize, right? So we have 2 options for that one. I'll do the L'Hopital's method first. So if I am doing L'Hopital's rule, I've shown that I have 0 over 0. L'Hopital rule states that the derivative of the numerator and the denominator will have the same limit. That denominator's derivative is 1. That numerator, so that's going to be 4x to the 1/2. So 1/2 comes down in front, 4x to the -1/2 times the chain rule of 4. That 6 goes to 0. And then I can go ahead and do direct sub. So I have the 1/2 4 square root of 4 times 9. You can leave your answer like that. Or simplifying that, that's going to become 2 over square root of 36, 2 over 6, 1/3 would also work. That's the new way to do it. The old way that we did it, I'm not going to work it out completely this way because you would have the same answer, is you could rationalize. And if I'm rationalizing this problem, so x is going to go to 9, this was the original limit that we had, and we would have to multiply it by the conjugate. And then it wasn't Hart's test, but then you had to like FOIL the numerator, factor it, cancel, and then plug it in. But you're going to get the same answer you do from L'Hopital's rule. Again, I won't tell you which method to do it. If you're comfortable using L'Hopital's rule, you can use it. If you just look at that problem and automatically think to rationalize and cancel, then you can rationalize and cancel. Questions on those problems? All right. Here's that flowchart back from Unit 1. I shared it with you just in case you wanted to look at it. So basically, L'Hopital's rule is just going to be another example where we keep going. And again, any method we use for like doing the algebra stuff or what matters most can also be done using L'Hopital's rule. So it's just like another option we have for finding limits. L'Hopital rule, though, does lend us to some examples that are just a little bit more strange. So that's kind of what the rest of the notes are going to look at. It's just kind of these like special cases and stranger kind of types of problems. So in this first one, I have the limit as x goes to 0 of this x squared plus 3x times the cotangent of x. So we know the first thing that we want to do whenever we're dealing with a limits question is to always try direct substitution. So this is x is going to 0. So when I plug in 0 for x, this first factor is going to become 0. The second factor is the cotangent of 0. Well, what is the cotangent of 0? Undefined. Why is the cotangent of 0 undefined? What's happening at the graph there? It's 1 over 0. You think back to last year, we know that's where a vertical asymptote is kind of happening on the graph. I know I'm only approaching 0 from both sides, but we know if we were to approach 0 from one side, it's either going to go towards like positive infinity or negative infinity. So this is the case where I say that this is a infinity times 0. I know we don't often think of like undefined as being infinity, but this is an undefined that's approaching an asymptote. So that's where the infinity kind of is coming from for this one. So right now we don't actually, like there's nothing we can do before changing it around to kind of solve that problem. But we can force this problem to be a L'Hopital's rule problem. To force it to be a L'Hopital rules problem, we want to find a way to rewrite the problem. There we'll go. So this is going to be the limit as x goes to 0. In order to do L'Hopital's rule, we want to kind of clearly see a fraction. So either that both the numerator and the denominator go to 0, or both the numerator and the denominator go to an infinity. What's one way I might possibly want to rewrite this problem so I can clearly see the fraction? Okay, so two options. So I'm going to go ahead and leave this up in the numerator. Two ways we can do cotangent. Cotangent we can think of as cosine over sine, or we can think of it as 1 over tangent. If my ultimate goal is to use L'Hopital's rule, I want to have like easier derivatives to find. And I would recommend using 1 over tangent as the way to rewrite it. Because if I wrote it as cosine over sine, I would have like a cosine in the numerator with that polynomial, and you have to use the product rule. So it's actually going to be easier if I think about cotangent as 1 over tangent. And again, you can't just jump straight into L'Hopital's rule, so you still need to check that you can use it. So plugging in 0, my numerator is approaching 0. And then I have the tangent of 0. Well, the tangent of 0 is also going to give us 0. So we can do L'Hopital's rule. So go ahead and finish out that problem for me. And so finishing out that problem, L'Hopital rule lets us take the derivative of the numerator and the denominator. The numerator becomes 2x plus 3. So as x goes to 0, the numerator is going to 3. The derivative, bless you, of tangent is secant squared. The secant of 0 is 1, so 1 squared gives us 1. This limit is approaching 3. So that's an example where we have to rewrite the problem. For the next example we're going to look at, one issue we sometimes run into when we want to rewrite a problem is there will be like multiple ways to rewrite a problem. We need to choose the best way or choose the way that gives us that indeterminate case that we need for L'Hopital's rule. So the next example I want to look at is this one, where I have the limit as x goes to infinity of x times the sine of 1 over 4x. Again, whenever you do a limits question, you always want to kind of make sure you do direct substitution first. So as x is going towards infinity, this first factor is going to go towards infinity. The second factor, so that 1 over 4x is inside of the sign. Ignoring the sign for right now, 1 over 4x, x is going towards infinity. What is 1 over 4x going towards? 0. So then what's the sign of 0? 0. So this is going to be an infinity times 0, which again in math is an indeterminate form. So we need to find a way to rewrite this to potentially use L'Hopital's rule. What's one way we can rewrite this problem so that we can see the fraction and use L'Hopital's rule?
X over cosecant 1 over 4x.
Say it again.
X over cosecant 1 over 4x.
All right, let's try it. So x will leave in the numerator, and then I know sine is the same thing as cosecant. Again, you just can't jump into using L'Hopital's rule, so we do want to make sure that this checks out and gives us an indeterminate case. Well, x is going towards infinity, so this numerator is going to go towards infinity. This denominator we'll need to kind of think about it. So 1 over 4x would still be going to 0. What is the cosecant of 0, though? Undefined. So we have infinity over undefined. Does that make us happy or sad? Sad, right? That's not L'Hopital's rule. We can't do it that way. So we're like, okay, well, that didn't work out. Let's find another way to rewrite that problem. So instead of moving that sign to the denominator, we can also move the x to the denominator. It looks weirder to do, but we know that we have the algebra skills to do that. So I'm going to go ahead and leave the sign in the numerator. When I move that x to the denominator, it's going to become x to what power? -1. So let's go ahead and make sure this works to use L'Hopital's rule. We already kind of did the numerator. 1 over 4x as x goes to infinity is going to go to 0. The sign of 0 is 0. So far, so good. This next one, I have x to the negative first power. In my head, how I'm kind of thinking about that, x to the negative first power is the same thing as saying 1 over x. Well, if x is going towards infinity, what is 1 over x going towards? 0. So this denominator is going to 0. Can I use L'Hopital's rule?
Yeah.
Yes, so go ahead and finish out that problem. Take the derivative of the numerator and the denominator. Again, just like with all of your derivative rules, if it helps you to rewrite stuff to make it easier, you can. Like I might rewrite the inside of that sign as 1/4 x to the negative first power. Take the derivative of the numerator, take the derivative of the denominator since we have that indeterminate case. Before you plug it in, you're more than welcome to like simplify that fraction and then try direct substitution. Make sure you use your derivative rules correctly. So I thought about the inside of sine as 1/4 x to the negative first power. Derivative of sine is cosine. Leave the inside the same, then times the chain rule. I do see some things that cancel out, like this whole piece cancels with that whole piece in the denominator. So now I can go ahead and take the limit of this one, except I did leave off something. Let me try my chain rule again. Left off my coefficient. The negative came down in front, 1/4 came across, x to -2. There we go, that looks better. So then canceling this one, the x to -2 cancels out, that negative divides out. So do substitution. I'm going to rewrite it just to clean it up a little bit. So I have a 1/4 times the cosine of 1/4x. X is going towards infinity, so 1/4 is a coefficient. This becomes the cosine of 0, and the cosine of 0 is 1. So this limit would be equal to 1/4. These are the ones that I think cause students some of the most issues with L'Hopital's rule, because you have kind of like two options in how we could have rewritten it. But we need to rewrite it so that the fraction we create gives us the indeterminate case that's allowed for L'Hopital's rule versus just some other messy thing that we can't do anything with. Questions on that one? All right, we'll just keep moving along. Here's where it starts getting fun with L'Hopital's rule. So L'Hopital's rule works whenever you have an indeterminate case. So say you're working on a problem, you get 0/0. So you apply L'Hopital's rule. You do direct substitution. You get 0/0 again. Well, what do? Just L'Hopital's rule again. And you keep doing L'Hopital's rule until you no longer get 0/0. The longest problem I've seen on a release question on the AP exam had you do L'Hopital's rule 3 times before you stopped getting 0/0. This one is not that long. I do think it gets trickier because sometimes some functions do get more complicated as you keep taking the derivative, whereas other ones do tend to get more simplified. This is one where we have to do repeated L'Hopital's rule. So again, we can check to make sure we're using L'Hopital's rule. Plugging in 0, that numerator is 0, the tangent of 0 is 0, so we can use L'Hopital's rule. So here's the first round of L'Hopital's rule. The limit as x goes to 0, 3x² minus 12x. Make sure you're using the chain rule when you take the derivative of tangent squared. So 2 comes down in front. Tangent's now raised to the first power. The derivative of tangent is secant squared. We think we're good to go. Plug in 0. Plugging in 0, we see that the numerator is, surprise, going to 0. 2 times the tangent of 0. Well, the tangent of 0 is already 0, so it doesn't really matter what secant is. So this one is going towards 0 as well. So now we're just like, oh, well, just do L'Hopital's rule again. Do need to be careful when you do the derivative in that denominator because this is a product, so you will have to make sure you use the product rule and hope that you don't have to keep using L'Hopital's rule. Well, let's go ahead and try it one more time. So I have the limit as x goes to 0. That numerator is going to become 6x minus 12. Looking at my denominator, so I have the first times the derivative of the second. The 2 comes down, leave the inside the same, then times the derivative of the inside, secant x, tangent of x, plus the derivative of the first times the second. Could clean that up a bit, but I'm going to go ahead and do direct substitution. Again, I'll clean it up if I get 0/0 again. Looking at this numerator though, 6 times 0 minus 12 is going to give me a -12. Looking at my denominator, I see I have a 2. Tangent of 0 is 0. The secant of 0 is 1. Like that whole first term is just going to go towards 0. But then plus 2 times 1 times 1, so that denominator is going to go towards 2. So what is this limit going to be equal to? -6. If I had gotten 0/0 again, then it would have just been me doing L'Hopital's rule until I eventually stopped getting 0 over 0. And theoretically, in this one, we could only take the derivative one more time before the derivative of that numerator just went to 0 itself. Questions or concerns for that one? All right, I have 2 more slides to do. Stay with me. We looked at examples in Unit 1 where we had kind of fractions with denominators with limits. Does anyone remember when we had limits with like multiple fractions, what we had to do to kind of approach those problems? What do we have to do? We got to get a common denominator because basically limits don't work nicely when you have like 2 separate fractions. They work better when you have a single fraction. Likewise, if I were to go ahead and just do my direct substitution, the natural log of 1 is 0. So this is pretty much going to be like a 1 over 0 minus a 1 over 0. I call this the case like infinity minus infinity because it's basically like an asymptote minus another asymptote, which means nothing in math. So similar to what we saw in Unit 1, we want to find a common denominator. And this was a Unit 1 question. You had to find a common denominator, combine your 2 fractions, refactor it out, cancel, and then do direct sub. This one's not going to cancel out nicely just because of that natural log term in there. But we can go ahead and find my common denominator, which is just going to be the natural log of x times x minus 1. And then my numerator would just be x minus 1 minus the natural log of x. Finish out that problem for me. First confirming that you can use L'Hopital's rule, and then performing L'Hopital's rule as many times as you need to until you stop getting 0 over 0. I'll go ahead and have at that one. I'll explain my work in a second if you're still working on it. There's my work for it. This one you do end up having to do similar to the other one, L'Hopital's rule twice. So after we got that common denominator, direct substitution, that first line that I have in blue gives me 0 over 0. So I can go ahead and use L'Hopital's rule. The derivative of the natural log of x is, of course, 1 over x. In that denominator, you would need to make sure you use the product rule. Some students might have distributed that natural log across first, but you still would have to use the product rule either way. And then that line in green is after applying L'Hopital's rule the first time. We do see again that we have 0 over 0. So we can use L'Hopital's rule again. As that problem, especially the denominator is written in green, that's kind of a messy derivative. So I would like distribute and then kind of rewrite it so I can just use the power rule. Taking the derivative again, that's what we see in my orange. We do see that that numerator then just becomes 1 over x squared. We're plugging in 1 for x, we get 1. And then in that denominator, we end up with 1 plus 1, or 2. So the limit for that one ends up being just 1/2. Did have to do like a lot of algebra there, so you have to remind yourselves, of course, to get like that common denominator. And then we ended up having to do L'Hopital's rule twice. Questions or concerns for that one? All right, one more slide, and it's just 4 problems. Just to make sure you understand how to do all of these. Try those 4 for me. For the sake of practice, some of these you can use other methods, but if you can use L'Hopital's rule, try to use L'Hopital's rule just for the sake of practicing it. But do always check, because some of them you can't use L'Hopital's rule for. But you should be able to answer all 4 of these now. Like we already got your derivative of a to the u. But not. There's the first 2 answers you should have gotten. So that first one, definitely if you were just back in unit 1, you would have factored and canceled. But using L'Hopital's rule, we have 0 over 0. So we have 1 over 2x could be the new function we're taking the limit of. As x goes to 1, that limit you should have gotten as 1/2. This second one, we get 0 over 0 again, so we can use L'Hopital's rule. There's not really another way to do this one without L'Hopital's rule, so I can take the derivative of the numerator and the denominator. Remember the derivative of a to the u rule, if you need the reminder of that, is the natural log of the base times exactly what you see, and then the chain rule is necessary. This one had just x in the exponent, so no chain rule was necessary. You do get the final answer for the natural log of 3. And then looking on that bottom row, that first one is the one that will be not L'Hopital's rule. That numerator is always between -1 and 1. That denominator is always growing, not very quickly, but it is always growing towards infinity. This one won't be one. Back in Unit 1, we would probably use like FEFL / like what matters most. Main idea of those, we have big on the bottom, so what is that limit going to go towards? 0. So that one would not be L'Hopital's rule. This last one I think is the trickiest one because you have to find the best way to rewrite it. So I do have the limit as x goes to 0 from the right. So x itself is going to be going towards 0. And then remember, we defined in the first unit that the limit as x goes to 0 from the right of the natural log of x is -infinity because of what that graph looks like for the natural log of x. So it is approaching -infinity. So this is a case where we have 0 times infinity, which in math is indeterminate. It doesn't really mean much for us. So we want to find a way to rewrite this problem. So if you want to find a way to rewrite this problem, there's 2 options you have. You either move the x to the denominator or the natural log of x to the denominator. Don't know which one it is until you try it, but I do recommend choosing the easier one first. What's going to be the easier one to move into the denominator? The x. If I move the natural log into the denominator, we have to worry about the chain rule. So we're going to hope that this works. To see if it works, you want to make sure you get the indeterminate case. Well, the natural log of 0 from the right is going towards what again? -infinity and infinity. And then we have x to the negative first power, so you want to kind of think to yourself, that's the same thing as saying 1 over x. So as that denominator gets super, super, super small, what is 1 over x going to be going towards? So think like x is going towards 0. So this is the same thing as, again, saying 1 over x. So think in your head like 1 divided by 0.1, 1 divided by 0.01, 1 divided by 0.0001. Is that getting bigger or smaller? Bigger, and it's actually going to go towards what? An infinity. And if you think about the graph of that, that might help remind you as well why it's going towards infinity, because there's an asymptote there on the graph. So we have an infinity over infinity. Can I use L'Hopital's rule? Yes, I can. So let's go ahead and use L'Hopital's rule for this one. So I have the limit as x goes to 0 from the right. The derivative of the natural log of x is 1 over x. The derivative of x to the -1 is going to be -1 x to the -2, or -1 over x squared. Looks ugly, but we know after doing L'Hopital's rule, we can simplify a problem. Dividing by a fraction, same thing as multiplying by the reciprocal. So this is really just the limit as x goes to infinity of -x, or should be 0 from the right, I should say. Where is this limit headed overall? It's just headed to 0 after we did all that work. Questions on that? So again, just like big idea with L'Hopital's rule, it only works when you have the indeterminate case of 0 over 0 or an infinity over infinity. If you don't end up with one of those fractions, you want to find a way to rewrite it to kind of force that indeterminate case to show up. Which time do I have? Oh gosh. Your homework tonight is just going to be homework number 5. I know I have a lot of words up there, but tomorrow is a teacher work day, so if you have time to work, feel free to email me or text me questions. Like, I'll be on my computer all day working. I did also share with you your briefcase binder stuff if you wanted to go ahead and start working on that. I do have some warm-ups for Wednesday and Thursday, but for the most part, Wednesdays and Thursdays is going to be a day for you again to finish homework, ask questions, and work on your briefcase binder stuff. So I know the bell's about to ring in like literally a minute, but definitely hang back and ask questions if you have them. Matthew.
How would you do if you have moved the natural log?
If you move the natural log file,
Why would you have to change it?
so it'll be the natural log race to the data. And also like you would so like that would be what you would think of as like this, and the limit was, so this would still be 0 over, that's going to be a 0. So it takes the derivative, this becomes 1 over -1 natural log of x. Like you get the same answer. So that's going to become.
Do we leave in this job?
Yeah, you can leave now. And so like this is still going to go forward. I just think it's easier to do it the other way. So you don't have to do all that.
Oh, so when you move L next, the X doesn't just go right?
No, like you're moving natural log of x as non-nerd becomes like the entire natural log of x to the negative first.